Hello guys, welcome back to Abstronic tutorial. Now let's discuss how the driver relay switch circuit working. So let me design the driver circuit to drive the relay switch. Now we have the driver relay switch circuit. Consists of 4 components: transistor, relay switch, the diode, and the base bias resistor. Let's connect the inductor of the relay switch to the collector and the anode of the diode. Connect the 5-volt battery to the coil and the cathode of the diode. Connect the negative battery to the emitter of the transistor. Connect one side terminal of the AC 220 volt light bulb to normal open terminal of the relay switch. Then connect the opposite side terminal of the light bulb to mirror plug, which is connected to the outlet. The common of the relay switch also connected to the mirror plug. The base bias resistor also connected from the same power supply, which is 5 volt. Before we calculating, let me inform you about the rated value of each component using in the circuit. The rated voltage of the relay switch is 5 volt and the power is 0.36 watts. According to the datasheet of BD139, the collector current is 1.5 amp and the DC current gain is 40 to 250, and the internal forward voltage is 0.7 volt. So when the 0.7 volt injected to the base of the transistor, the collector emitter will be activated. But when the voltage applied to the base is less than 0.7 volt, the collector emitter will be cut off, meaning the base current controlling the collector emitter current. To calculate the base bias resistor, let's apply the formula IC equivalent to IB times the beta, which is the current gain of the BD139. First step, calculate the current of the relay by using the power formula. Then calculate the base current. Then the voltage drop at the base bias resistor. Now, let's begin calculating the circuit by using this formula. IC equivalent to beta, which is the current gain of the BD139, times IB, the base current of the transistor. Then simplify the equation IB equivalent to IC divided by the current gain, which is the beta. According to the datasheet of JQC, the 3F relay switch, the core power equivalent to 0.36 watts and the core voltage 5 to 48 volt DC. So therefore, the collector current must be equal to the current of the relay switch or greater than the current of the relay switch. And to calculate the rated current of the relay switch, let's apply the power formula to calculate the current. Then substitute the given value to the power formula. The power of the coil, according to the datasheet, is 0.36 watts, equivalent to voltage, which is 5 volt times the current of the relay switch. Then simplify the equation. IR equivalent to 0.36 divided by 5. IR equivalent to 0.072 ampere or equivalent to 72 milliamp. Since the current gain of the BD139 is 40 to 250, let's choose 250. Also, you can choose the collector current equivalent to 72 milliamp or greater than 72 milliamp. So let me choose 112 milliamp. Then IB equivalent to IC, which is 112 milliamp divided by beta, which is 250. IB equivalent to 0.45 milliamp, and now we can calculate the voltage drop at the base bias resistor. BR equivalent to 5 volt minus the internal forward voltage of the BD139 for silicon, which is minus 0.7 volt. Therefore, BR equivalent to 4.3 volt. Now, we can calculate the base bias resistor by using the Ohm's law formula, voltage equivalent to I times R. Then, simplify the formula. R equivalent to voltage divided by I. Right now, we can substitute the value of the IB and the BR to the formula. R equivalent to 4.3 divided by 0.45 milliamp. So, the resistance equivalent to 9.5 kilo ohms. If 9.5 kilo ohms is not available, you can choose 10 kilo ohms resistance. So let's inject IB 0.45 milliamp to the base of the transistor. So what happened to the transistor when 0.45 milliamp injected to the base of the transistor? The collector emitter resistance will be decreasing, and when the resistance decreasing, the ground begin attracting the positive current from the battery, and the battery releasing 75 milliamp, and this current flowing to the coil of the relay switch and going out from the opposite of the coil, entering to the collector and going out to the emitter and going back to the ground. And the light bulb right now is glowing. This circuit is the continuation of my previous project, how the latching switch circuit working, which is the part 3. You can watch my previous video. I just put the link in the description below. What about the diode which is connected to the pin of the relay switch? The diode used to protect the transistor from the back EMF from the coil of the relay switch during the power is turned off. When the power is turned off, the coil begin inducing high voltage. And this voltage can destroy transistor. Since the diode is connected in the circuit, therefore the transistor will be protected. So, let's turn off the circuit. Now, we have no voltage injected to the base of the transistor. The inductor begin inducing high voltage from the internal of the relay switch circuit. Now, you can see the magnetic field expanded and the current direction is the opposite of the battery. Since the anode of the diode connected to the positive voltage of the inductor and the cathode of the diode is connected to the negative of the inductor, so therefore the diode is forward biased. So when the diode is forward biased, then the current from the inductor flowing and entering to the anode of the diode and going out to the cathode and going back to the negative side of the coil. Then the transistor will be protected by the diode simply because the current flowing to the diode and going back to the negative sides of the coil instead of going to the collector of the transistor until the magnetic field collapsing and disappear. Now, let's connect the driver relay switch circuit to the output of the latching switch circuit, and let's see on my breadboard circuit.